Hello, this is a presentation on the calibration of Transmon superconducting qubits. My name is Stefan Titus. So as we learned during the guest lecture, the Transmon superconducting qubit behaves similarly to a quantum harmonic oscillator, but it uses a nonlinear inductance. The nonlinear inductance causes it to have some anharmonicity, that is, some deviation from behavior as a pure harmonic oscillator. This creates non-equidistant energy levels. So we can see here the blue is a quantum harmonic oscillator, and the energy levels are equal distance. But in the orange, we have the behavior of a transmon. We can see that the energy levels are getting closer together. And this is important to us because we need to be able to excite the qubit from state 0 to state 1, but not from state 1 to state 2 or higher states. On the diagram up here, we have a number of inputs and outputs. There's the XY input, which is used to rotate the qubit state around the XY axis. And there's another Z input, which is used to rotate it transversely, but we're not going to be really addressing that here. There's also a resonator, which is coupled to the qubit that is used to read out the state of the qubit. And that has an input and an output that is amplified. All of this is inside a cryostat on the order of 10 millikelvin, which is required for silicon to behave as a superconductor. So let's talk about how a single qubit gate works. All single qubit gates, at least working with the XY input, are just varying pulses applied to that input. So a sine wave at the resonant frequency of the qubit will cause the state to rotate, and we can create a specific rotation by creating a pulse of that frequency. So we can't have that pulse turn on and off immediately because the transients of turning on and off would contain energy components at other energy levels, which could move our qubit into a higher state of 2 or 3 or higher. So instead, we use a Gaussian shape to the pulse, which reduces the transients of turning on and off. The actual pulse shape is not quite a Gaussian. There's a more optimal shape, but we're not going to go into that here. The actual oscillation comes from a local oscillator, which is just a low phase gigahertz range sine wave generator. And the pulse shapes are created with an AWG, which is an arbitrary waveform generator. It's essentially just a really complicated digital to analog converter. But the thing that's doing the magic is the IQ mixer, which you can think of as multiplication, or you can think of it as amplitude modulation. And that allows us to create a pulse at the target frequency with the desired shape. The in-phase signal will rotate the qubit around the x-axis, and the quadrature or out-of-phase signal will rotate it around the y-axis. But that's just by convention. By tuning the pulse length and amplitude, we can rotate the qubit by a specific amount. But what we really care about is the integral of the pulse envelope. So we can change either the pulse length or the amplitude. In this presentation, we're going to be talking about changing the pulse length, but in reality, it's usually more convenient to adjust the pulse amplitude for reasons that we're not going to get into. So let's talk about the steps needed to calibrate a transmon qubit. The first step is to measure the resonance frequency of the readout resonator. So we do this by generating a frequency sweep going into the resonator line here, and we measure that on the output here. And as you can see in the chart, there will be a dip in the amplitude where near the resonant frequency of the resonator. And we just want to find that frequency. And we just need to plot the data and apply a fit line to find the resonant frequency. The next step is to measure the resonant frequency of the qubit. Again, we use a frequency sweep, but this time we go in on the XY line and we read out through the readout resonator like before. Again, we're going to plot the amplitude of the signal we get out and find the peak. This time it's a positive peak. The next step is called the Rabi experiment. What we're trying to do here is calibrate the pulse we put into the XY so that we know what pulse length will produce a rotation by pi. We drive a pulse of some length into the XY line, and then we use the readout resonator to read the state of the qubit. When we collapse the wave function of the qubit, we only read a 0 or a 1. So in order to get these in-betweens, we need to repeat the experiment, say 1,000 times, and average it together. We repeat this experiment again across many pulse lengths, and then we plot the average result against the pulse duration, and then we fit a sine wave to the data and find the peak, which represents the pulse length needed to rotate our Bloch sphere by 180 degrees, or pi. In the next experiment, we need to begin quantifying the decoherence of the qubit. When we excite a qubit to the 1 state, it will randomly decay to the 0 state. So to measure this effect, we initialize to a 1 state, and then we wait some time tau, and then we read out the qubit state. Again, we get either a 0 or a 1, so we repeat that many times to get an average. And then we repeat that across a range of values of tau to get a plot like this. And we can plainly see an exponential decay. And we just find the 1/e decay point, and that is our time constant, t1. The next experiment is quite a bit more complicated. What we measured with the previous experiment was decoherence along the z-axis. And with the Ramsey measurement, we want to measure the decoherence along the xy plane. This is also called transverse relaxation or transverse decoherence. So the scheme to test this is we start by applying an x pi over 2 pulse to rotate from the 0 state down to the y-axis. And then we're going to wait some time tau, and then follow with another x pi over 2 pulse. And if we had no decoherence, then that would bring us right down to 1 every single time. But there will be decoherence. So when we rotate by our x pi over 2, it will bring us not quite to 1. So then we will usually get a 1, but not always. Again, we need to repeat the measurement over a range of tau, and we get a chart something like this. But there's a lot going on here. The first thing we need to account for is the energy relaxation from the previous experiment. So I said that with no decoherence, we would come down to the 1 every time. And that's not really true, because in our previous experiment, we saw that sometimes a 1 will flip to a 0. So we need to account for the effects of T1, but there's also a number of other noise sources, and some of them behave exponentially. Some of them are broadband noise that creates a Gaussian component. But in any case, we do need to extract those effects from each other and find the exponential fit. And again, we find the exponential decay T2, which is the time constant of the exponential components of the transverse relaxation. There's a number of other noise sources here that we're skipping. So I haven't talked at all about 2-qubit gates yet. And I'm not going to say much about 2-qubit gates because calibrating a 2-qubit gate depends entirely on how those 2-qubit gates are constructed. And every lab, it seems, has a different way of constructing them. So we're not going to talk about a specific approach here, but suffice it to say that it's more complicated than all the stuff that we've talked about so far. So how do we quantify the overall performance of our system? The gate error is 1 minus the gate fidelity. And the gate fidelity is essentially how close the measured state is to the desired state. We know how to find the desired state with a simulation, but how do we measure the actual state? To do that, we use a technique called quantum state tomography. And you may have encountered the word tomography before. If you've ever had or heard about a CT scan, that is a computed tomography X-ray scan. And in that case, it's taking multiple 2D X-rays and combining them into a 3D representation of your body. In this case, we're doing something roughly analogous, but we are measuring the qubit along 3 different basis vectors. Now, when we've been measuring the qubit state before, it's been along the z-axis. We're getting either a 0 or a 1. But this doesn't give us any information about the azimuth, where it is in the xy coordinates. To fully characterize the state of a qubit, we need to measure it on 2 other bases. And it's good to use orthogonal bases, but if all we can get is non-orthogonal bases, we can solve for orthogonal bases with some math. So how we actually do this is we perform our experiment, and normally we measure it along the z-axis. In order to measure it along the y-axis, we rotate a quarter turn on the x-axis and then measure on the z-axis. And to measure along the x-axis, we rotate a quarter turn about the y-axis and then measure on the z-axis. But the major downside for this is that it does not scale well for multiple qubits. When we measured 1 qubit, we needed to measure it on 3 basis vectors. When we introduce a second qubit, that's 3 additional basis vectors that we need to measure across. So the total number of experiment setups we need for n qubits is 3 to the n. And remember, we also need to run each experiment setup, say, 1,000 times. So that's 3,000 experiment runs for 1 qubit, 9,000 for 2 qubits, 27,000 for 3 qubits, etc. Obviously, that's not going to be feasible for large numbers of qubits, and large turns out to be something like 4. So what we use to get around this is a technique called randomized benchmarking. With this, we're looking for a sequence of gates, a quantum circuit, that will always return back to the initial state, if the gates were perfect. If the gates are not perfect, then it will end up in some other state. So all we need to do is execute that circuit a bunch of times and count how often we get the initial state and how often we get something else. Then we repeat this with many random circuits of varying length. And then for each sequence length, we average together all of the sequence fidelities for that sequence length. And then we plot that and we fit to an exponential, and then we find the time constant of that exponential decay. And that is our R, and we can use that to find the average gate infidelity. And this is useful for characterizing the complete system with a single number, but with more advanced benchmarks, we can do much more. We can find which gates and which qubits are contributing most to the error, and even which parameters we may need to tweak to solve the error. So where is this technology today? Quantum computers need calibration. They need continual calibration. Some of these parameters only need to be calibrated once. Some need to be calibrated by the hour or by the minute, or preferably continuously as the device is functioning. This isn't like a traditional system where we calibrate it in the factory and then ship it out and maybe calibrate it once every 2 years. What we're going to see in the future, in order for quantum computers to come to market, is these calibration procedures will be built into the device itself. The calibration is a core part of the quantum computer. What I see today is that randomized benchmarking remains a very active topic of research. In fact, my employer, Keysight Technologies, recently acquired a company called Quantum Benchmark that is doing exactly this. But overall, my impression is that while calibration is vitally important, it is not advancements in calibration that are holding quantum computers back from deployment. And these are my sources. The first source, A Quantum Engineer's Guide to Superconducting Qubits, was by far the most useful and comprehensive source. The second source here is the original paper that introduced the Transmon architecture. This third source is a summary of quantum state tomography. This fourth resource is about randomized benchmarking. I also used some material from a Wikipedia article on fidelity of quantum states. And special thanks to Clayton Crocker here at Keysight, who helped me understand a lot of this material. Thank you for your time, and have a nice day.